Hi everyone. As I have told you last week that we have to take some classes of our last second semester quantum mechanics. We have just started the class and had given a small introduction about the quantum mechanics. I have just introduced the Schrodinger equation to you, which is the basis of the fundamental equation from which we built up the quantum mechanics. There were several scientists who worked behind quantum mechanical theory. It is actually a theoretical approach to calculate the total energy of the electron and the probability of meeting electrons. Here we start with the Schrodinger wave equation, and we use a function called psi, a wave function called psi. We normally use this notation to represent the wave function of the electron. As I have already told you that electron as a subatomic particles means smaller particle than an atom. Electron, proton, neutron, etc. are subatomic particles, smaller than atoms. So we are talking about an electron, so it is actually a particle, and this particle, if the size is in subatomic level, it will show both particle characteristics as well as wave characteristics. Wave characteristics does not mean that the wave is not like electromagnetic wave, but it shows the wave characteristics. So here de Broglie, you might have heard about de Broglie relations, lambda divided by h by p, lambda equal to h by p, h is equal to Planck's constant, and p is the momentum and of the particle, and then the momentum is mass into volume, is the basis of explaining the wave particle dualism of freely moving material particle. So de Broglie, from the equation derived by the de Broglie, lambda means the wavelength of the material, matter. Lambda equal to h by p. So from this equation, scientists were worked on de Broglie's work, and then they were Schrodinger actually he derived his fundamental equation from taking the idea of the de Broglie relation. And Erwin Schrodinger demonstrated that the above concept would be generalized and applied to bound particles such as electrons in atom. Bound particle means if an electron is present around the nucleus, that means it is bound to the nucleus, and the electron is under the influence of the nuclear force. So that kind of particles are called bound particles. And if we take the case of Earth, it is also a bound planet because it is under the influence of the solar force. The Schrodinger recognized a parallelism between the behavior of the electron in a hydrogen atom under constraints imposed by the attraction of the nucleus. So this is what I said, as the particle size decreased to nano or less than nano, or if we talk about subatomic particles, the behavior of these particles are totally different. It is not just like Einstein's theory of relativity. In fact, Einstein was talking about macromolecules or macro objects, just like the planets with the gravitational force, Newton's gravitational force. Okay, so when we go more deeper into the matter, the behavior and the properties of the material or subatomic particles present over there is totally different. So whatever the laws applicable in solar system or bigger planets is not applicable to the electrons, protons or neutrons. That is a major difference between quantum mechanics and classical mechanics. It is now considered as a standing wave system. That means a wave that does not travel in space. It is not traveling in the space. It is not just like electromagnetic wave. That's what I told you just now. Exemplified by a vibrating string fixed at both ends. If you fix a string on both ends and then you just vibrate it, then that is just like a standing wave. It will make a standing wave. It will cannot propagate to the outer side. So it will propagate there only. The wave form will propagate there only. So for our convenience, we normally take it is a standing wave system. 1926, Schrödinger proposed a wave equation describing the electron's motion analogous to that used to describe a standing wave system. So in 1926, Schrödinger did his PhD, and in his thesis he proposed electronic motion is almost like a standing wave, and this equation is known as Schrödinger wave equation. The equation proposed by, or the way Schrödinger considered electronic motion as a standing wave, is known as Schrödinger wave equation. It is regarded as the fundamental equation of quantum mechanics. We have already discussed it. It is now generally accepted that the results derived from it are in remarkable agreement with experimental outcome. As I told you, quantum mechanics is completely a mathematical determination of the energy of the system, or talking about theoretical treatment of the electrons. So the theoretical treatment should be in agreement with the experimental results, then only it has the validity. Otherwise we cannot say the theoretical treatment is right. So here it is a whatever Schrödinger or the quantum mechanical theoretical explanations are in remarkable agreement with experimental results. So now I'm just introducing the Erwin Schrödinger. This is Erwin Schrödinger. So he is a physicist, and de Broglie. You might have seen the picture of de Broglie. He is a physicist. Both of them are physicists. They are mainly playing with the nucleus or subatomic particles. So he is an Austrian theoretical physicist who contributed the wave theory of matter and to other fundamentals of quantum mechanics. He shared Nobel Prize in 1933 with P.A.M. Dirac. I'm not sure whether you heard about Dirac. So you learn about Dirac after maybe in your higher studies. And de Broglie is a French physicist and who made a groundbreaking contributions to quantum theory. And in 1924 PhD thesis, he postulated the wave nature of electrons and suggested that all matter has wave properties. All matter, subatomic particles particularly, have wave properties. This concept is known as the de Broglie hypothesis. It is an example of wave particle duality. That is what I told you. Electrons can be a particle and also a wave, behave like a wave, and forms a central part of the theory of quantum mechanics. De Broglie won Nobel Prize for Physics in 1929. He completed a PhD in 1926 and Nobel Prize in 1929. At the age of 27, he got Nobel Prize. 92. 37. At the age of 37, he got Nobel Prize. Okay. After the wave-like behavior of matter was first experimentally demonstrated in 1927. I just want to show you the wave characteristic, how they are representing the wave characteristics for electron. This is the classical picture of electron in motion. Actually, we just consider this sphere as electron. So this is a particle, just a particle, nothing else. So it will show the particle nature. But de Broglie said in 1929 in his speech, Nobel Prize speech, we thus find that in order to describe the properties of matter as well as those of light, we must employ waves and corpuscles simultaneously. Corpuscles is material, particle, simultaneously. We can no longer imagine the electron as being just a minute corpuscle of electricity. We must associate a wave with it. So electrons can be considered as a corpuscle, and also it can be considered as a wave. Now we are coming to the topic, the time independent Schrodinger equation for the matter wave propagating in 3-dimensional space associated with the motion of the particle of mass m. So if an electron is moving around the nucleus of, then Schrodinger equation is expressed as di square. So this is a double differential equation, di square psi divided by di x square, x coordinate, di square psi by di y square, y coordinate, di square psi by di z square plus 8 pi square m divided by h square e minus v psi equal to 0. So psi is the wave function, as I have already discussed, and di square x by x square, di square by y square, di square by di z square is a double differential of the equation of this wave function psi. 8 pi square m divided by h square e minus v psi equal to 0. So this is the fundamental equation from which the quantum mechanics is made by Schrodinger. Okay. So x, y and z are the three three-dimensional coordinates. Psi is the wave function of the electron, and m is the mass of the electron, h is the Planck's constant, E is the total energy of the electron system, and v is the electrostatic potential energy, and psi is the wave function. So here he has used a double differential in order to give the position of the electron. Here the first three terms are double differentials of the function psi with respect to x, y and z coordinates respectively. The function psi depends on the coordinates of the particle, is called wave function of the particle. The wave functions are thus solutions to the Schrodinger wave equation. So he just put psi as the wave function. So what is the wave function? That is the wave characteristics of the electron. So once we have to solve psi, then that is the solution of the properties of the electron. E equal to total energy of the particle, V equal to electrostatic potential energy. So the functions of the coordinates, so these two are functions of the coordinates x, y, z of the system, and h is the Planck's constant. The wave function psi is a measure of the amplitude of the matter wave. Psi, as we told, is a wave function. It is just amplitude of the wave. So as you know, a wave will move like this, and then the amplitude from the center we have to find the amplitude, and this is just representing the amplitude of the matter wave associated with the particle at various points defined by the coordinates x, y, z with respect to a certain reference frame. So just keep in your mind, psi is just representing the amplitude of the matter wave. Okay. And as we had seen time independent Schrodinger equation, here we are going to see time dependent Schrodinger wave equation. From this he has derived time independent Schrodinger wave equation. Here time is also coming as a coordinate in addition to x, y and z. Okay, so as we represent electron is moving, so time will also coming as a coordinate. And if we consider only a standing wave, only the position x, y, z is only coming as the coordinates. So here h bar square by 2m di square by di x square psi, they have taken psi outside, or we can write it as di square psi divided by di x square. So here it has taken outside, di square by di x square plus di square by di y square plus di square by di z square plus v x, y, z, three coordinates of position, and then time, fourth coordinate, psi equal to minus h bar divided by I di psi by di t. So this is the final form of the time dependent Schrodinger equation, and this equation potential energy term depends on the four coordinates, and the wave function psi also depending on the four coordinates are both functions of time too, in addition to the coordinates x, y and z. Here we can substitute h by 2 pi h bar. So we are coming to say how h bar is coming. H bar means h by 2 pi. So h bar square equal to h square divided by 4 pi square. Okay, and this equation in fact constitutes one of the important postulates of quantum mechanics, which form the basis of the systematic treatment of atomic and molecular problem. So in order to describe the properties of the electron, subatomic particles, particular electrons, we use this Schrodinger equation, which is a fundamental equation for the quantum mechanics. And the time independent Schrodinger equation is obtained from the time dependent equation when it is separated into equations for the time and space variations of the wave function. So this time dependent wave equation, time dependent wave equation can be separated as equations for time and also equations for the space, x, y, z coordinates, and also for equation for time. So we can separate it into two. Okay, and for our convenience and more easy to solve the issue, we have to take electron as a standing wave. So we don't need to take time as a coordinate. So time constraint we can avoid. So in most problems related to atomic and molecular structures, we are concerned with stationary or standing waves for which there is no time dependence for their potential energy or the wave function psi. Okay, so next is operators is an integral part of the quantum mechanical functions when we describe, and we will discuss it later.